I'm Kim Edwards with the Teacher Enrichment Program, and we are here for STEM Careers Mechanical Engineering. I'll start off with our sponsors because we frequently do not get to this slide at the end. This session has been sponsored by Akamai Technologies, Aerojet Rocketdyne, Amazon, Amgen Foundation, BAE Systems, Corning Incorporated, Gilead Sciences, Illumina Foundation, Jacobs Engineering, Lockheed Martin Corporation, Psychmedics Corporation, Spark Therapeutics, TC Energy Foundation, TE Connectivity, and the Vulcan Materials Company. Okay, so I am with the Center for Excellence in Education, founded in 1983 by Joanne DeGennaro and Admiral Rickover, father of the nuclear Navy and civilian use of nuclear power. And our mission is to nurture high school and university scholars to careers of excellence and leadership in STEM. We offer 3 cost-free programs to students and teachers in the United States, which are the Research Science Institute, the USA Bio-Olympiad, and the Teacher Enrichment Program. So for the RSI program, Research Science Institute, it's a highly competitive 6-week summer science and engineering program open to rising high school seniors. They do a lot of coursework and then do some research with some professors, and participants generally go on to do well at Regeneron, the Regeneron STS, Siemens competitions, and many go on to advanced STEM degrees. For anyone who is interested, registration opens in mid-November with applications due in early January. We just went through our selection process. And then for the USA Bio-Olympiad, it's actually the nation's largest biology education and testing program. And they are actually currently in the middle of their semifinals. So it's a series of examinations on biology concepts. So the top 20 attend national finals, and they'll actually be right here in Northern Virginia at Marymount University. And the top 4 from that go on to the International Bio-Olympiad. And then for any teachers out there who teach AP or IB biology classes, they have some phenomenal resources. So I absolutely encourage anyone to get in touch with them if you're doing biology. And registration for students and teachers opens again next fall. And lastly, we have the Teacher Enrichment Program, which is what I'm here for. And our mission is to provide opportunities for middle and high school teachers to connect with experts in academia and industry, explore some cutting-edge research and development, and hopefully provide some information and resources that are helpful for you teachers and your students. This school year, we are still going virtual. So we're doing some virtual bites of science. We're doing these STEM career panels, which I'm really excited about. And we do a monthly Square Root of STEM event. And upcoming, actually, April is Genomics Month. So we are partnering with Illumina to do 2 genomics events. All the information is on our website. And since you've registered for an event today, you'll probably get an email invite about this. So we post all of our resources and videos on our Lab Bench website, which is just, if you go to the TAP website, it's right there. If anyone's interested or needing connections to industry or universities, STEM resources, please just let us know over at TAP, and we're happy to help you out. And I actually should say, this is actually my last event with CEE. I am leaving CE to help my mom with some stuff at home, and actually joining me off screen is my replacement, Travis. So I'm super excited to have him here with us. So for those of you who have seen me for the past 2 years on video, it's been wonderful, and I will miss all of you, but certainly, keep in touch with TAP. They know how to get in touch with me if you ever need anything. And today I am really, really excited to have Michael Scibelli, who's program manager for ship repair at BAE Systems, and Adam Laakmann, chief engineer at Aerojet Rocketdyne. And with that, Michael, it's all you.
I'm Mike Scibelli, and from BAE Systems, I am a program manager these days, but I got an engineering background, so I'll get into that here. So just start off, had a pretty cool picture here on the front. This is the Norfolk, Virginia waterfront here as we look out at our Pier 1 facility here. So this is the first time that the Navy put 2 destroyers in a dry dock. So what you can see are the wing walls of a floating dry dock here. And so when you want to do ship repair maintenance on a vessel, you put in a graving dock, which is like a big hole in the ground with a gate that you can flood it, or you got a floating dry dock like what we've got here. You can sink it down, ballast it down, put the ship in on a bunch of wood blocks, cement and wood block combination, pick it back up, and then you got a ship, you can work on it. Not every ship that we work on goes in the dock, but a lot of them do when you want to work on certain aspects of it. So just a pretty cool image. Again, first time the Navy put 2 destroyers in a single floating dry dock. It's a pretty cool event for us. A lot of engineering went into this to kind of figure out where the ships were going to sit, how they needed to sit in relative to all the work that we're going to be doing on it. So a lot of planning in that regard. But just a pretty cool image, big accomplishment for us, the company back in the 2010 time frame. So today I'll take you through, who's talking. That's me. What we do here at BAE, kind of where we do it, just for some background. Who does it? Who are the people that we have on staff, as well as the engineers. We do have a small engineering staff at the sites, but then just kind of my perspective and where I've come from, what I've been able to do and work on as part of a team member here at BAE, and sort of how STEM has played a role in that. So I actually started my career, my first job out of college was at Newport News Shipbuilding. So that's basically a new construction yard. It's actually right across the river from where I am now in the Hampton Roads area, but mostly working on new construction aircraft carriers. So pretty cool place to work, cut your teeth as a young engineer. I worked there for about 7 years doing a lot of machinery type projects. And then I came over to BAE. It's a little bit closer to home, across the water, didn't have to sit in tunnel traffic all the time. So came over as a principal engineer and worked in an engineering role here in BAE for about 5-6 years, and then more recently transitioned kind of the program side. Again, coming to the BAE side, I've got to do a lot of different things here. So that's kind of where I'll kind of highlight towards the end. And then just as a background for me, so I went to school in upstate New York at a engineering school called RPI. Some people know it, some people don't, but so RPI grad probably 2007 time frame. I got my professional engineer license a couple years later. You got to have some time under your belt before you can get that licensure through whatever state you're practicing in. And then went back to school, got an MBA, and eventually got a program management professional license. So that's kind of helped me transition to the program side. That's kind of me in a quick nutshell here. But so again, just BAE. I work for BAE Systems ship repair, the ship repair sector. So in our name, that's basically what we do. We fix ships, all U.S. Navy non-nuclear surface combatants. So that's destroyers, cruisers, amphibious class ships. Some vessels that do some really cool stuff. We predominantly work for the U.S. Navy. Occasionally, we'll get a commercial vessel in the Norfolk Yard, but not very frequently. We compete with some of the bigger defense contractors, but in our area, it happens to be a lot of the smaller ship repair entities that we compete with. But just as a primer and info to what BAE does, none of this is quite STEM related, but just for awareness. And what we like to say is our discriminators, like you saw on the front slide, is we have floating dry docks, we have piers, we have cranes, and ship repair is a pretty capital intensive environment, and you need to have all those types of facilities to really execute the projects that we do. So this picture here is actually pulling a rotor out of a generator on a vessel. And so you can see, we've cut a big hole in the ship. We've made this yellow fixture, that somebody engineered, make sure it could pick up the right amount of weight and all the configurations that that this thing has to move as we lift it up. And then somebody's rigging it up. We got a rigging crew that's picking this thing up out of the space. So that's what ship repair is, right? You've got a vessel that's been constructed, maybe 10 years ago. It's coming in for a dry dock. You got to tear the thing apart. It's kind of equivalent to a home renovation, right? You got to tear your kitchen apart. You got to rip out all the old cabinets. You got to put the new cabinets in. But to figure out how to do all that stuff, takes a big effort, right? Picking up where everything that you pick up, is probably a couple thousand pounds. You got to figure out how to do that safely. And a lot of times that involves, designing a special piece of equipment like you see here, this yellow thing that, is simple in nature, but pretty critical. We've got a saying in the engineering group, is the thing mom-proof? Would you let your mom stand underneath the thing while it's being raised up? And if you say no, then you probably need to do some more push-ups and figure out your design a little better. But where we work for BAE, so we've got a site where I'm sitting today in Norfolk. We've got one down in Jacksonville, Florida, and then we also have a location out in San Diego, California. And so all told, we've probably got about 3,000 employees across the 3 sites. We got 5 dry docks, 2 marine railways. That's kind of another way to pull ships up out of the water. 17,000 feet of pier space. I think that's square footage, not linear feet. All told sites, a couple sites across the country that, we all do about the same thing, a little bit of nuance between the sites. And then, right, so who does the work? I kind of highlight this because there's so many elements or so many trades, skilled trades and functional roles that are engaged in this process. And really, as you know, from my perspective as an engineer, I get to get engaged with all of them. So whether that's the inside or outside machine shops, or the riggers, or the sheet metal department, or plate fitters, you know, people that are welding things together, the structural folks, or even the carpenters, you know, the engineering role here, at least in my particular site, you know, is hey, you're the technical SME for everything that goes on. And so if something's not you know, up to snuff, you know, it's kind of our job to say, hey, that's not the way to do it. We need to figure out a new process, we need to design a new tool or a new fixture. So that's been a great experience here at BAE for me, anyways. That you know, you get a wide array of things that you can work on, and I think that's one of the benefits of mechanical engineering is there is so many opportunities to go in a lot of different directions and have an understanding of many different facets and trades. I kind of highlighted too, just because, you know, I thought it was worth mentioning, you know, we certainly struggle to fill welding roles and quality inspectors. Those are roles that we have a hard time filling. And right, a weld engineer is a role that we have on hand, and those are very hard to come by in some cases. And so whether, you know, you like mechanical engineering, right, you get a pretty broad perspective, or, you know, welding engineering is obviously very focused. You know, they're in very high demand. Just, you know, felt like you know, felt like it was important just to mention in general in our industry, you know, welding is a very critical trade. It's probably 60% of what we do is hot work related in some kind, so whether that's cutting or burning or welding. So you know, as a thought of your mind, hey, if you wanted somewhere that's going to guarantee you time in the future, you know, engineering front, get involved in welding engineering or mechanical engineering, right? You can kind of go anywhere, but those are high demand, those areas anyways. So with that also, that's kind of the BAE primer, but I kind of picked a few things that I've gotten to do here at BAE that I wanted to highlight. And so, you know, metrology is a big thing these days, where you've got these specialized tools that you can go out and take very high precision measurements of various components. So, you know, we use this tool called Spatial Analyzer, and you can kind of see this like mock-up plate. It's got two handles on it in essence, and you see these three sort of machines in the background. You got a laser tracker, a scanner, and an arm that are measuring this piece of equipment. And this is representative of things that we do here. We've got a piece of equipment kind of like this one on the left. Do I have a cursor? I don't know. The one on the big stand on the left with the head on it, that's got the majority of the lines coming from it. But so a tool like this, a laser tracker, right, you can take out on the deck plates, you know, onto the ship, and you set up in an area where maybe there's a critical piece of, you know, weapons systems or countermeasure equipment that really has to have high tolerances in order to function properly. And this piece of equipment will allow you to go out and scan the surface, you know, where it's going to be mounted, or maybe scan a couple surfaces and determine the relationship and the angles between those two surfaces, you know. And to do that, right, you know, the tools these days are becoming ever more intuitive and simple to use. But where the engineering mindset really comes in is interpreting and understanding those results. So you're going to get all these pretty colors, and you're going to get these graphs, and you can learn to do this without much of a background. But you know, when it push comes to shove, and you have to interpret some of these results and figure out, hey, is this meaningful data, or did I have error in my data? You know, did maybe at the start of, you know, my measurement session, I was at 20 degrees because it's in the middle of winter, and then, you know, the sun came out and started beating on the deck plates and really warmed up all the steel, and steel, you know, tends to expand and contract in temperatures. And so now at the end of my measurement session, because it took me all day, my steel has, you know, grown and expanded however many, you know, even at this scale of measurement, right, a couple of tenths and hundredths of an inch make a difference and sometimes in the acceptance criteria of installing that equipment. So, right, understanding the tooling that you're using, you know, understanding some of the way that the tool was designed, that's really where the engineering mindset comes in, and having that mathematical background to kind of figure out and do some spot checking, you know, of those measurements. So, hey, okay, I had a 20-degree temperature swing. You know, some basic equations that I can figure out. If my steel should have expanded this much, I got to compensate for that in my measurements. And the tools can do that, but you have to be able to know kind of what those environmental conditions are that may impact it, and also how to set up the tool initially, how it's measuring and understanding that geometry. So that's one cool thing that I've been able to do is use a tool like this and go out and do some precision measurements. But it's the challenging part. The fun part is going out, taking the measurements. The challenging part is, okay, now I've got all this data and I've got to sort of scan through it. It's potentially many numbers of data points that I have to review and sort of give it that thumbs up, thumbs down. Do I agree with what it's saying? Do I understand, what the results are, and have I set up my constraints and assumptions appropriately? So one example of kind of what I do here, and then another one that I thought, is pretty prevalent, across a lot of industries, but we do it here as well when we get into some of our design work, which is finite element analysis. And so this is just kind of an image I picked up offline. But what it represents is, again, some computer programs when you're designing components, you can do an analysis, and the computer system will tell you, hey, here's where the stresses are going to be observed in your component under certain loading conditions. And so this is kind of a stress strain. Well, it's probably just stress curve and contour of whatever this component is. So somebody would have had to model the component in 3D, and that in my industry or in my location would have been the engineer, right? So you use a 3D program to draw this component. You set up some loads, some constraints, some material properties, and then you let the machine spit out the results for you. And again, just like with the analyzing tool, you have to be able to understand these results. And at an elemental level, when you see kind of all these triangles around this component, that's a mesh that the computer has just defined on this piece, and it's basically just breaking it up into lots and lots of little. In this case, I think it's a tetrahedral mesh, and that's just a certain shape, right? So you've got these tiny shapes and triangles that the computer is then running through all these iterations of calculations and figuring out at these nodes and in these elements, what is my stress? Because that's what engineers are really concerned with in component design. Hey, what is the stress of the component? Is it going to break, or is it not going to break? And is it going to break after 50,000 iterations, or is it going to break after 5 iterations? That's what we're really interested in when we do a lot of our design work. And at a individual level, right, you can run through the calculation yourself and figure out a stress at a particular location, but it's pretty time consuming. So the computer certainly aids that these days, and these tools are very intuitive, again, to use, but understanding your results is where the engineering mindset comes in again. And if you can't visually see, right, that, hey, I've loaded it in this direction and I'm seeing stresses really high at this particular location, if that doesn't pass sort of just your basic engineering understanding, right? When you go back to your, kind of core engineering classwork of, okay, if I take a beam and I bend it this way, I'm going to expect this stress. You can really apply those fundamentals when you look at stuff like this, and to be able to understand, do I have my constraints appropriately set up? And so, we may do something. You saw the picture earlier on when we were lifting that rotor, and so that we may do an FEA. It's a pretty simple kind of lifting fixture. We may not need this level of granularity, but if we have something really complex that would take a long time to analyze by hand, we'd punch it into the computer, let the computer do the heavy lifting. But that discerning judgment is really where what you need to have in order to have a safe design, because you can't just assume that the computer knows what you want and knows the lifting conditions. So some guided help. And all of this, I was thinking about the laser tracker kind of example and this example. And, the thought for me is I wish I knew more math. I took a lot of math throughout engineering coursework, but if you expect that you're really into design and you want to go and design cool things, I think as much math as you can get is probably good, right? There's differential equations, and there's linear algebra and multivariable calculus. And if, those people that work at SpaceX and NASA and maybe even Adam too, working with rockets and stuff, right? Math is so critical to a lot of these types of projects, of understanding how the systems are figuring out results when you work with these kind of computer programs. And in hindsight, for me, I said, I'm in that elective that I took, art of film or whatever in college. I probably should have taken another math class. instead and gotten a little bit better there. So, but so that, I also want to just kind of hit on the program management side, right? So I've made a transition, at least in my career, from the tech side to the program management side, but wanted to sort of tie it together because a lot of what I do on the program management side these days does have that math element to it. And I think engineers, right, not to say that we should go out and be mathematicians, but, have that strong math background and end up doing a lot of math. I mean, data analytics is a big part of what we do these days and where a lot of companies are driving. And certainly in my role now as a program manager, trying to deploy systems that crunch a lot of the numbers, for our projects. And so for other project managers to be able to understand. And so it's all right, compilation of data, condensing into nice, pretty dashboards like this. But again, it's that understanding of how you get this set of information and understanding where these numbers come from and being able to kind of spot check and say, yeah, that should be what we expect in those numbers is crucial. And then the other side in the program world, right, if you do happen to go that route, is just understanding the state of your project. And so on the right, this is just sort of a representation of kind of earned value metrics. And right, so you've got cost and time, but you're looking at your planned value, your actual cost, your earned value. And these are very simple metrics to come up with, but it's all formulas and math that you need to work out to say, hey, yep, I'm under budget, I'm over budget, or I'm behind schedule, I'm on schedule. And these are pretty widely accepted practices of how to track schedule progress. So even on the program side, I guess as I was thinking through, where does my STEM, has STEM really done for me? It's been on the math side. That's kind of been the long-standing thread as I've transitioned in the program world. It's been consistent, throughout my career so far. So I think that's kind of the last bit here, and I'd certainly take some questions if there were any.
What would you say the hardest math you do every day is?
These days, as a program guy, it's not very hard anymore. The earned value stuff is, one number over another number, some division. But, if I went back to my early career days were mostly in the design world for new construction, right? You're doing, you issue a drawing out, and behind that drawing, you have to have supporting calculations for whatever that is, right? So you would have, you'd be working with a designer who's kind of mocking up whatever it is, and then you're, working out the fundamental or the calculations behind it. So that's a lot of stress strain type analysis. I think in the FEA world, right, you do a little bit of that by hand, but the hardest thing that I've ever done, I would say, I had to do a longitudinal shaft vibration analysis for the aircraft carrier that I was showing in the front. And so those have been done, over a number of years for all the different carriers that are out there. But we were working on a new class, so you had to do a new analysis, and that was like setting up a big group of kind of mass damper systems that hey, as you interact with this end of the shaft, you have vibration that's going to resonate through your shaft line. And figure out, is it going to shake the ship, to pieces? Because that used to be a problem, early on in like World War I and II, more so II, I think, as we were just pumping out ships, right? We'd have all these natural resonances in shafting that would shake the ship, and we learned a lot. The country learned a lot, and our engineers learned a lot during that time period of having ships have those issues. And today it's something that's built into our design practices to figure out, hey, this is the natural resonancy, and that's not going to be within the operating range, or any, kind of echoes of that resonancy where we operate. So that was probably the hardest analysis I've ever done. Took me like, I don't know, probably 3-4 months to finish that one.
Oh, actually, well, actually, this might be. What does BAE actually stand for?
So it's one of those 3-letter, I don't even want to say acronym, but it is not an acronym anymore. At one point in time, there was a British Aerospace and I think an Electronic Systems that did come together, but today, BAE does not stand for anything. So it's just BAE Systems. Yeah.
That's fine. And then what's been your favorite project to work on?
Favorite project. So I worked on the last big repair project that I worked on was so the USS Wasp is an LHD class ship, and they had a casualty event where they overpressurized one of their ballast tanks. So the Wasp is can submerge the aft end of the ship and then open up a big gate and let all these amphibious vehicles out. And so they have all these ballast valves they can flood certain tanks, and they actually overpressurized one of their tanks, and water pressure is pretty incredible, and they actually blew out the side of the tank, deformed a bunch of structure within the tank, and sitting right above that tank was the machinery for the aircraft elevator. So the elevator that brings the planes up and down from the flight deck to the gallery deck, for storage. And so, we had, as BAE, we got the repair job for that, and had to cut out all that damaged steel, replace it with new structural members. And in doing so, we didn't want to disturb the alignment of that aircraft elevator ram. A huge, hydraulic ram that opened and closed like a big piston. And so we had to develop all these temporary shoring members to support that weight up top, and we did routine measurements of the foundation and make sure that was staying level as we cut out various sections. And so that was a pretty complex job where we worked in sequence to replace various structural elements. And part of that was taking a chunk of the ship and figuring out, hey, I've got these loads on these beams, so I need to support it with these types of members. And then make sure I don't have any undue deflection and misalignment that I'm going to cause up on the decks above. So.
Awesome. And I guess, I would imagine this would vary depending on the size of the project, but I guess how many people actually work on like a single project?
Yeah, so we've got, in the Norfolk site, right, I showed we got about 1,200 people that are on the facility, and out of that, there's probably 900 or so that are skilled trades. And depending on the availability, you would have you could have as few as 15 or maybe even 2 that are working on maybe, if you got just an emergent job that you had to fix one thing. But typically our availabilities are somewhere between 9 months and a year. And then our workload would sort of vary from, a peak of, could be as many as like 600 of that 900 effort that are working on the ship at one time, with probably a project team that's maybe 25 or 30. That might be on the high end, but so it's going to fluctuate, again, depending on the complexity they avail. But some of these bigger ships can pull 600 or so of our workforce, plus a small contingent of project management folks. So pretty large group.
Oh, thank you. What would be your best advice to give to a high school senior who wants to be a mechanical engineer?
Like I said, definitely keep taking those math classes. And I would say, if your school's got opportunities for like FIRST robotics or any of those kind of extracurriculars, those certainly look good as you start applying for schools. I was, I guess, thinking back as a kid, right, it was, built a lot of stuff, took a lot of things apart, that was kind of, if you've got those similar kind of background, things that you like to do as a kid, that was, built a lot of Lego stuff, model rockets and whatnot. I just always kind of said, hey, I think engineering's the choice for me. And so, you go in undeclared, right? You don't declare mechanical until, maybe sophomore year, depending on your school, but never switched, always was an engineering major anyways.
Now I'm laughing too because I know some other mechanical engineers, and as a kid, they took a lot of stuff apart.
Yeah, I think that's a requirement actually. You have to take things apart.
Do you get to travel at all?
Yeah, I do. I mean, you saw the 3 sites. We used to have a Hawaii location, a San Francisco, and a Mobile, Alabama. And so, in my time here, I got to go to Hawaii, I got to go to Mobile. I never made it to San Francisco, but I have made it to San Diego. Our site had kind of that expertise in the laser tracker system and metrology end that our other BAE sites did not. So as we sort of stood up a group to work that at those sites, we would travel and sort of kind of do some knowledge transfer in that regard. So yeah, have had the opportunity to do some travel.
And well, I mean, actually, so I studied in Rensselaer, which is a great engineering school. I'm from the Northeast, so that was always one that people always talk about as being great. But I guess sort of, I don't know if you know anything about sort of universities that have really great mechanical engineering programs.
Yeah, I mean, RPI obviously is number one in the country. But no, I think probably MIT still probably has. Yeah, I mean, was that the Gators? I don't know who's ranked the best. I would not get so hung up on rankings. I think you can find a good engineering program across the country close to you. There's certainly some prestige if you go to MIT, right? People look at you differently, I think, if you go to MIT, but I think you can get the same amount of knowledge, in most places that you would go. I mean, there's certainly, some programs that, maybe have something to be desired, but I would not begrudge, a school that's close to you just because it doesn't have the name of MIT. That's my perspective anyways. I think there's probably a lot of great professors and a lot of great teachers and a lot of great schools that you could go find. But I think just do your due diligence when you apply, right? Kind of maybe seek out some of the students that are there and see where those students end up career-wise. If they're getting job placement out of college, which I think is pretty accessible as an engineer to do so. I think that's kind of really the telling part, right? If people are getting starting their careers out of school, that kind of speaks to the program.
Yeah, and I mean, to echo someone else who does hiring for engineers. I can't remember actually what company it's for, but he does a fair amount of hiring. It wasn't necessarily the university or college they went to. They were looking for really the degree, the experiences that they had, anything extra that they participated in, during their college time, what classes they took, really. And I think the other thing he had talked a lot about was people who are really interested in learning more, and taking what they've already learned and applying it in new ways and learning how they do it at their company. So to echo that. And to encourage any students who maybe are interested in this. So last call for questions. A really chatty group. Have fun. Oh, one more. You know anything about biomedical engineering?
I had a few. RPI has a biomedical engineering major, and so I knew some biomedical engineering students. In my time there, I would say very promising. Right there is always medical. My wife works in sort of the clinical trial area, and so I see some of that. And there's always new devices coming out, and while they take a long time to go through FDA sometimes, that's a very lucrative area, and not that that's the driver to get into biomedical engineering, but you can do a lot of cool things in that field, and I would say it's promising. There's a lot of opportunity out there for that major for sure.
Yeah, to echo that, I actually have a good friend who was a physics major in college, graduated with a physics degree, and then went back for a master's in biomedical engineering, and is fabulously successful. And having seen a number of biophysical, people who study biophysics, the physics portion is very helpful for biomedical engineering.
Yep.
And again, I mean, if any students out there, I've listened to a lot of these presentations. A lot of it's just, what are you interested in doing? What makes you excited to learn? That's really, really important to, I think, employers especially. They want to see passionate people who are excited about what they do.
Yeah, you cued just one memory of mine that I have to add. I had a guy or a buddy in school that was a physics major because he wanted to be a roller coaster designer and go work for Disney, as a roller coaster. So I would have thought, hey, mechanical would have been better for you, but he said, no, physics, is the way to go. You get a physics degree, maybe even a doctorate of physics, you go design roller coasters with that. So, at least the layout anyways.
Awesome. So thank you so much, Michael, for presenting. It was fabulous. BAE certainly does many, very, very interesting things. And with that, we can just send it right over to Adam.
Hey everybody, I'm Adam Laakmann. I'm a recent transfer to Chief Engineering at Aerojet Rocketdyne. For folks who don't know what Aerojet Rocketdyne does, we're one of the nation's two now solid rocket propulsion providers, and we also do liquids. Anything rocket propulsion or energetics, Aerojet Rocketdyne does. So how I got into engineering, I'm also a mechanical engineering from the other best school, University of Florida for mechanical engineering. No bias there. When I was in elementary school, I lived in Orlando, and there's a cul-de-sac at the end of our block that if you walked out to it, there was no houses developed there yet, and you can see straight down to Cape Canaveral. I was 50 miles away, but you could see straight in that direction. So every time they launched the rocket or a space shuttle from there, we'd go down to the end of our street and we'd watch them launch. We'd see it a few seconds after liftoff by the time it cleared the horizon, but we'd go out there and watch them all the time. And I thought it was the coolest thing. So from a very young age, I was into rockets. I didn't know at that time that's what I wanted to do. In elementary school, I was like, I'm going to be an astronaut. I gave up on the policeman and fireman thing, and I was like, I'm going to be an astronaut when I grow up. But anyway, I grew up. I haven't become an astronaut yet, but was still always interested in space. So I guess we go to the next slide. When I finished elementary school, we moved down to South Florida, down to the Fort Lauderdale area. And down there in Broward County, they had a pretty good magnet program, a pretty healthy magnet program at their different schools. One of them happened to be at a school I was districted for. So by high school, I ended up going to one of the science pre-engineering magnet schools they had down there, focusing on the pre-engineering track. So I took a lot of kind of engineering geared courses there, a lot of math, science, physics, chemistry, and the like, kind of in prep for college. And in high school, when I was close to graduating, I was going to be an aerospace engineer. That was my original plan. I saw someone ask a question earlier about changing majors. So I kind of did, but before I even started college for real. I went to a summer program at the University of Florida between my junior and senior year, and they basically took high school students from around the state and paired them up with other engineering or science departments at the University of Florida. And the one I got paired up with was in the mechanical engineering department. And there was a grad student I worked with there who talked me out of aerospace engineering and talked me into mechanical engineering. And the reason for that was aerospace, the industry kind of has ups and downs. There's times where there's lots of work, and there's times where it's not so much. And if you happen to graduate college at the wrong time, there might not be a job in aerospace waiting for you. But as a mechanical engineer, not only can you just as easily get a job in the aerospace field, but if the aerospace field is down here, you can get a job in automotive industry or in air conditioning or in shipbuilding. Anything that involves machines, there's jobs for mechanical engineers out there. So I took that advice. And when I ended up going to college, I went to the University of Florida after that for school. And when it was time to declare my major, I went and declared mechanical engineering. Still ended up getting a job in aerospace as it turned out. Got my bachelor's degree in 99, went out looking for a job. Industry was down near the bottom. It wasn't a big aerospace hiring spree when I got out of school. So I was sitting around for a little bit, this close to going back to Dairy Queen, which was my pre-professional job for 3 years while I was in college. And as it turned out, I ended up lucking into a job in aerospace. Long story there, but worked out well for me in the end. Been doing rocket propulsion since. So yeah, I hired into Pratt & Whitney in West Palm Beach. I think it talks about that on the next show. So I started at Pratt & Whitney in West Palm Beach, Florida. That branch of Pratt & Whitney, most people think Pratt & Whitney, they think of the jet engine business. That is Pratt & Whitney's biggest business. But in West Palm Beach, they had a smaller space business as well, making liquid rocket engines, mostly upper stage stuff. So smaller engines than what you'd see like at the bottom of the space shuttle or the SLS. But I started off working there. I actually interviewed for jet engine jobs there when they called me up, and the rocket thing was an aside. At the end of the day, the guy who was taking me around from interview to interview with the jet engine managers asked if I wanted to talk to one of the rocket managers. We had a free half hour at the end of the day. I was already dressed in a suit and drove up to West Palm Beach from home. So figured as long as I'm there and, all dressed up, figured what's the harm in it? So I talked to him. He happened to also go to the University of Florida. We talked about football for half an hour and he hired me. He ended up hiring me. And that's how I got into rockets. So when I say I lucked in, I pretty well did. But I've been doing it since. It's what I like. It's what I love, even since I was a kid. always been into rockets. So I was very fortunate to be able to get into the industry and be in it since. I did a few years at West Palm Beach at Pratt & Whitney, and then I moved on to the solid side of the business, solid rockets, starting with ATK in Maryland, which is the other solid rocket company besides Aerojet now. They've since been bought up by Northrop Grumman, so they're part of Northrop Grumman. But I worked there for about 5.5 years before transferring over to Aerojet. And I started Aerojet 2010 in Sacramento. In 2018, I moved over to their current defense headquarters in Huntsville, Alabama, where I'm at right now. Okay, so what does a chief engineer do for Aerojet Rocketdyne? I'm still trying to figure that out myself. I've only been a chief engineer there since the beginning of November. For 11 years before that, I was a ballistician, completely different field. But the chief engineer, whereas previously I was an analyst, I was responsible for specific parts and specific jobs. Now as a chief engineer, I kind of oversee other engineers on the programs I work. I'm like the chief engineer is the technical lead for a program, or several programs there. So they kind of oversee the analysts, the designers, all the other engineering staff. The chief engineer kind of is the lead of that group. Keeps them focused, makes sure they know what tasks they're working on, helps kind of deal with problem solving at the high level if they run into issues, helping set priorities for what the engineering team needs to do and focus on, and also interface with program management, kind of serve as the cushion between the engineers doing the work and the program office. A lot of interface with the customers as well, which can be good. Sometimes it's a little harrowing depending on the customer and the program you're working on, but chief engineer has to deal with them a lot. Usually there's a chief engineering counterpart at our customers that I interface. They're the good ones to talk to, the technical minds at the other companies. But on the downside, there's a lot of time spent in meetings. When I was a normal working engineer, when I did ballistics, I didn't spend nearly as much time in meetings as I do now. So kind of sad about that. Still getting a feel for the chief engineering position, falling into that job, but I do miss the real work a little bit. Being down in the trenches, and I miss not having calendars full of meetings from sunrise to sunset. But getting into the swing of it, as Michael mentioned earlier, math is real important in any engineering job, certainly. Math is kind of the language that ties everything together. Any engineering design work you do, any analysis work you do, there's other, skills involved. Physics is a big one. Some of the sciences, depending on the field you're in, chemistry or metallurgy. But at the end of the day, math is kind of the foundation that you need for pretty much any engineering job. When I did ballistics, it doesn't have to always be complex math either. I took way more math in college than I ended up using in my jobs that I've had since. In my previous, when I was a ballistician, like the most complex math that I did, it went from simple geometry, just being able to draw shapes and visualize how they grow as propellant burns. A little bit of trigonometry, basically resolving thrust off at an angle, how much of it's pointed in the X direction, how much of it's pointed in the Y direction, and very, very little bit of calculus, basically week one of calculus type stuff. So even in rockets, there's jobs where need math, but it doesn't always have to be the highest echelons of math. Although there are positions within the company that helps. Some of the more theoretical type work involves a lot of higher math, stuff beyond me. Good foundation and just the technical basics. This just, again, applies to the job I'm working now, but any engineering job in general, and a lot of jobs just in technical fields. Just a basic understanding of physics, chemistry, depending on what you're doing. If you're working with energetics and things that burn or things that get hot or cold, thermodynamics is a good thing to have a good understanding of. You might need to know about materials, a little bit of material science, mechanical design principles. At the end of the day, though, you don't need to be an expert at any of this. As it turns out, with most jobs, As long as you have a good basic understanding, that company is going to teach you everything else you need to know. Most schools don't teach rocketry. They don't teach, anything more than just the fundamentals, basic fundamentals of rocketry. Not enough to go out and design rockets. And companies know that. And they don't want you to come out of college thinking that you know how to do everything. They want you to just have a good base understanding, and then they're going to teach you everything you need to do, to be able to successfully do your job that they hire you for. So most of what you learn in school, at the end of the day, you probably will use. But you don't know that until you get the job that you get when you come out of school, because some subset of everything you learn is going to be necessary for every job. I didn't end up getting a job in rockets. Some of the other things I learned in college would have been necessary. Stuff that I don't use now, I might have used in a different job had I hired in at a different company when I started. Or even if I'd worked on the jet side of Pratt & Whitney instead of getting hired into the rocket side, I would have used different skills that I picked up in college than I did on the rockets. Good to have a good basic, education, especially in mechanical engineering, because mechanical engineering is such a broad field. It's not as focused as, say, like an aerospace engineering or chemical, where they focus on specific, fields of engineering. Mechanical is really broad and it covers a wide range of opportunities. So you get a good broad education, which is why it makes it so marketable when you're, out there trying to get a job. Having that mechanical engineering background, the companies that are interviewing and see your resume know that you got a good broad education and it wasn't just focused on one little aspect. Most important piece of advice I could probably give to anybody, not just students or not just folks that are trying to get out into the workforce, but know what you know and know what you don't know, and don't be ashamed to ask anybody for help or admit that you don't know something, because people more times than not are more than happy to help you and educate you on what you don't know. It's much better than thinking you know a lot and then being smacked down by humility when you're shown that you don't know as much as you think you do. And there's no shame in asking for help. I've been working in rockets for 23 years now, and I still ask people for help. There's still plenty of stuff I don't know, and I will happily admit it and go talk to the people that know the stuff, and ask them for help, ask them for advice. Even to this day, even my mentors, the people that trained me up, the old graybeards that are knocking on retirement's door, they know they don't know everything and they still ask. It's always important, just good general advice in life. Know what you don't know, and don't be shy about asking people to help explain it. So if anybody out there or any of your students are interested in a career in rockets, I highly recommend it. I love it. I love every bit of it. It's although after watching Mike's presentation, ship repair seems pretty awesome. I won't lie. I was sitting there glued to my screen watching that. As a mechanical engineer, any mechanical things fascinate me. But if you want to get into rockets, there's simple ways to kind of pad your stats when both looking at a school or when you look to come out of school and get into the workforce and try to get a job in rocketry. If your college has a rocketry club, participate in any extracurricular activities, even at the high school level. Mike mentioned like first robotics. That's a good thing. I used to judge that at the middle school level when I was in Florida, and things like that. Any team type projects are good because companies love somebody that can work on a team, because that's pretty much what work is. You're going to be collaborating with a lot of different people from varied fields, and being able to function on a team is a top-notch skill to have. If your school doesn't have a rocketry club, be about starting one. I know a lot of people that work with me now at Aerojet. They came from schools or colleges that didn't have big engineering programs or focus on rocketry, and they just started their own rocketry club. Stuff like that impresses the interviewers when you go to apply for jobs at rocket companies, propulsion companies. Connect with professionals in the industry. The best advice you'll get about getting a job in a certain field is from people that are in that field. They can tell you what the job's going to entail. They can tell you what they did in school, give you advice on what, would help you as a student be able to better position yourself to get into a good engineering program or into a good engineering job. Seek out mentorships. They don't have to be formal mentorships. Doesn't have to be anything, formal set up. It could just be an informal mentorship. If you know somebody that's in the field, or just reach out cold on, go to career fairs or STEM fairs if they have any. And even just go creep on people on LinkedIn. I've had a lot of people that ended up getting hired. College students would reach out to me on LinkedIn just out of the blue. Strike up a conversation, ask questions. I'd give them advice back, and down the road later, they ended up working. It's good to make those kind of connections too. Shows an interest, and also helps give them a source for advice. Help them learn what the industry is about, if they're still interested in it, and what they might do to better position themselves. And in college, once you guys get to college, I know there's a lot of high school teachers here, I believe, in middle school maybe, but later on when the students get out into college, the industry is really competitive right now. This is the aerospace industry is really high on the hiring phase right now, and there's a lot of competition for jobs. So internships they're almost a must, and they're good, to spend the summer. Most of them pay. So, if you're a poor, starving college student, you've got a good summer job that probably pays pretty well, and it gives you experience, gives you real world work experience, sometimes even in the industry you want to get into. And having that on the resume when you go to apply for a job later on really helps a lot right now. It helps filter those resumes and help. If I were to apply for a job today, coming out of college, I'd be a Dairy Queen. It's gotten that competitive now. So I tell a lot of the kids that I interview coming out of college have resumes that just blow mine out of the water when I graduate. Some of them have resumes that probably blow mine out of the water today. But yeah, there's a lot going on. But it's very competitive, and making sure that you take advantage of the time you're not in class in school to get involved with extracurricular activities. And even go out and get those summer jobs, try to find those internships or co-ops that build the experience, and give the student, a sense of what working out in the real world is going to be like, how to work on a team, what kind of dynamics there are with the folks that they'll be working with once they go out into the world full time. I think that's all I've got in here. Anybody have questions?
Yeah, there are some questions. For mechanical engineering, is the job market so competitive?
I'd say right now it probably is. I think that there's a lot of companies and a lot of industries that are having a difficult time finding people. They have a lot of openings, but there's also a lot of applicants. I am usually to some extent involved, especially my former position in my last group. I helped my manager out a lot, helping him sift through resumes from college students, particularly for both internships and graduating students looking for full-time jobs. And we just had stacks and stacks of resumes to go through. And again, that's where having those internships is critical. I didn't have any internships, so it was hard for me to go and try to, put aside resumes from students that didn't have, internships on their resume or as much. But, at the end of the day, someone who's had an internship has worked. They've worked in industry before, or at a company, and they already have a feel coming in for how to operate in a work environment. So that's one less thing they would have to adjust to coming in. But I think in other industries, so I live in Huntsville in Alabama, and in that area, there's a lot of work. It's a big aerospace town. You got the Redstone Arsenal there. You got NASA's Marshall Space Flight Center, Missile Defense Agency. All of the aerospace primes have a big presence in Huntsville. But there's also a lot of automotive manufacturing in the Huntsville area. Mazda Toyota just opened up a huge factory that is going to ultimately employ something like 4,500 people building Toyotas and Mazdas. Toyota's got an engine factory that's right next to one of my company is one of Aerojet Rocketdyne's factories. There's a lot of chemical industry work right down the road from Huntsville and Decatur, and they're all competing for a very limited number of people to work. There's a lot of work that's coming in, and most of those places are hiring. So I would say that just in general, industry is pretty competitive, not just aerospace, but other industries as well. Yeah, they're have a lot of openings, but there's even more people that are applying for it, especially college students coming out, trying to get into industry for the first time. So it is pretty competitive. I can't say which industry is more competitive. I know the aerospace industry just that's the one I'm in, but kind of cursorily, the automotive, they're suffering kind of the same thing. A lot of jobs in certain places, and yeah, and a lot of applicants for those jobs, kind of competing to get them.
Yeah, what would be so could you tell me, like, what's Aerojet Rocketdyne having a hard time hiring for? So I know because you mentioned Huntsville, but and I've talked to people at like Lockheed Martin, and they can't find machinists or welders.
We are hiring across the board. We can't get enough people fast enough. There's a lot of work. Like I said, the aerospace industry is at a high. And when the aerospace industry is at a high, it's because there's a lot of money that is available to feed into it for new programs or existing programs. So, Aerojet, we're looking for engineers a lot. But we're also looking for, engineers. We work one side of the business, right? Primarily the design side. But for production programs, right? Once a program's designed, we win that contract, we design a motor or whatever it is, someone's got to build it. So we also have a lot of openings at our manufacturing facilities for, anybody from welders, composite technicians, people that are familiar with rubber, machinists. If there's a job involved in making rockets, we have probably open requisitions for people to come work those jobs. And we're having a hard time finding bodies to fill them. There's a lot of cannibalism going on in the industry right now too. As companies are struggling to find people, they're going to the experienced people, that they already know, and they're kind of poaching from each other a little bit, trying to find experienced people.
Oh, sure. And I actually want to combine two questions, because I think they're similar, related, but not the same. What would you say? So you are now in this leadership position, but you did some engineering. I mean, I've met other chief engineers in leadership position, and sort of what would you say is the most important skill to have sort of throughout your engineering career? And then what's an essential skill that you've had that's helped you in this new position?
So I'll say again, I think the most essential skill to have in any engineering position is knowing what you don't know, and being able to ask somebody for help when you know. It's not like a sign of weakness. Some people are kind of hesitant to go ask for help. They take it as a pride. It's like, I'm an engineer, I got this degree, I should know these things, and nobody can know everything. So in my career, I came out of college, a bachelor's in mechanical engineering. I had one propulsion class that focused mostly on jet engines, and it was an elective. It wasn't even part of the mechanical engineering required curriculum. And of that propulsion class, there was this much on rockets and this much on solid rockets. So I came out into the rocket world not knowing really anything aside from, burn propellant and thrust comes out the back. So I asked a lot of questions coming up. And again, I still ask questions. The programs I'm working on now are beyond my area of expertise. And as a chief engineer, I'm not expected to know all the technical details of how to design and make all these parts. I just have to kind of know of them. But I know the people to ask who are the experts on all these different components, and the people to go to, and I need someone to design a part or analyze a part. So yeah, being able to go and ask those kind of questions, find out the things you don't know, after you do, then you know them, right? You've learned something. And engineering is kind of a continuous learning experience. And most people that get into engineering are happy about that. People get into engineering, as mentioned, they like to take things apart. Why do they like to take things apart? Because they're curious. You know, if you know, especially mechanical engineers like to see how things work. And that's not something you really lose over time. There's still plenty of stuff I don't understand how it works. Try to figure out how to get the Zoom meeting on my kid's laptop running. I learned that on the fly today. But yeah, just being able to go out, reach out to ask people things you don't know is important. What was the second part of that question?
I mean, actually, well, it's kind of also like, so like just broadly for your engineering career skills, but also like, you know, now in this.
What's helped me in this job? Chief engineering, social skills. I'm a pretty talkative guy at work, get around and socialize with folks. So I knew a lot of people from before, just chatting around folks, really just killing time. You know, if I needed to get away from my desk, go lean on somebody's wall and shoot the breeze. But it's helped a lot because I'm working with different people than I'd worked with for the last 11 years at Aerojet. So being able to go and kind of knock down that wall of, you know, I'm a chief engineer, you know, I'm above them, I kind of direct things and kind of knock it down and make it more of a comfortable situation for me to be able to communicate with them and for them to feel free to communicate with me. You know, kind of just, yeah, making situation, communication is pretty essential. Being able to share with your team, you know, what your needs are, what your problems are, instead of kind of keeping that back, because then it doesn't help anybody if that kind of stuff doesn't get out. So I go around, I talk to all my my team members, or call them across multiple sites. You know, I met a few of them for the first time today. I'm out in Virginia on business travel, sitting in a lovely hotel room here. Yeah, some of my team, I've been working for them for the last 4 months. I'd never met them before in my life, so I made sure while I was out here to go and find them and talk with them. But that's helpful. You don't have to be a social butterfly per se, but you know, just being able to reach out. You got to reach out to folks and be able to talk with them. I think makes for effective teams, and that's helped me a lot. Switching over to this chief position. This is really my first foray into you know, being in charge of people.
You're almost out of time, so I actually have a very random question for you. Since you work in Maryland and you work in Rocketry, we actually had a guy named Jacob Temme from U.S. Army Research present, and I don't know if you happen to know him.
That broke up again.
What?
I didn't hear the last part.
Oh, Jacob Temme. He works for U.S. Army Research in Aberdeen
Okay.
on combustion research for the government.
Okay.
I don't know if you ever happened to meet him in your rocketry circle.
Oh, no, I haven't. I'm sorry. Yeah. It's a small industry, but it's also a big spread out industry. But yeah, I have not met. I'll say I haven't met him yet.
I always like to ask people those random questions because I've had events where they're like, there's two researchers and I'm on like, you know, human microbiomes. And they're like, oh my gosh, you work in so-and-so's lab? Oh yeah, I've worked with them forever. And it's a very small research world out there.
I've had a lot of instances of that, where, you know, I'd be talking to some stranger somewhere and we have some common person that we worked with different times in different places, but it's like, I know so-and-so, or, you know, some people that I worked with years ago end up showing up. When I started at Pratt & Whitney in West Palm Beach, it was kind of an independent thing. It was just part of Pratt & Whitney. But since I moved on, and now that I'm at Aerojet, Pratt & Whitney merged with Rocketdyne, which is based out of LA, another liquid rocket engine company that makes the space shuttle engines. Since then, Aerojet bought Pratt & Whitney Rocketdyne, that combined company, which included the West Palm Beach facility. So all the people I worked with when I came out of college and started with in 1999, I now work with them again. And now they come up to Huntsville from time to time. And I see all these guys I haven't seen since 2005. I left Pratt & Whitney. and now they're coworkers again. You know, I've been toying around the idea of, like, you know, seeing if Aerojet would transfer me back to West Palm Beach, just so I can be closer to the beach again, and see if I get my old cube back, because it's probably still sitting there, you know, looking the same as it did when I left it. And the people that I sat next to are probably still in the same cubes next to me there.
You
So
don't
yeah,
know if you'll never know if you don't ask.
it's kind of weird sometimes. You know, the rocket industry is pretty tight. It's not a very huge industry, and I lost the sunlight outside, some clouds rolled in. But yeah, it's very interesting, the people that you run into at the most random times.
All right, that is all the time we have. I want to thank you, Michael, so much for presenting. Adam, thank you so much for presenting. I feel like I've spent a lot of time this past month learning a lot about mechanical engineering. So I now know more than I've ever known before. I feel like if someone asked me what do mechanical engineers do, I could finally answer them. So thank you all so much, very much for joining. It was a fabulous last event for me to host, and I hope to work with some of you in the future.